Good morning, everybody. Today is my lessons on fluids. Do you ever wonder, is sand a fluid? Is Jello a fluid? What makes a fluid a fluid? Is everything the same as water or gas? Let's take a look. So if we take a look at all the substances of the world, we know that they are composed of three different states of matter. We have solids, we have liquids, we have gases. Right away, off the bat, solid is not even considered a fluid. It just is the shape. It does not change the volume. It is what it is. However, liquids can be divided into two separate categories. The liquid can be, we call that incompressible fluid, and gases are compressible fluid. And we will see why in just a minute. So if we take a look, fluids, what are they exactly? Well, they are substances that have the capacity to flow and assume the shape or the form of the container naturally without any additional force. So anything you can think of, you pour it in and naturally just flows in and takes up the shape. So here are some of the examples. Water, of course, liquid water, I should say, maple syrup, milk, motor oil, compressed air, Cheez Whiz. If you squeeze Cheez Whiz, the one that's squeezable will take up the shape of the container easily. And so sand is not a fluid because even if it flows easily, when you pour it in, it does not always take the shape of the container unless you shake it. And here's an example in that image. If you notice, I pour in some sand and it'll make like a small mountain like that, but unless you shake it, it will never budge. And that's why sand is not considered a fluid. Don't mix fluid and liquid. Okay, be careful with that. Really, it's really a fluid means the substance can flow naturally and assume the form of a substance, of a container. So if we dig deeper into the incompressible fluids, so they are liquids because their volume cannot be changed. They cannot be squeezed into a smaller container. The particles are loosely packed and have weak forces of attraction, so they can slide over each other to take on the form of their container. And this is all due to the fact, if you see that image at the bottom, that there's barely any space between liquids, and so that's why it's really hard to compress. There are some scientists that say it is possible to compress a liquid, but with tremendous amount of force, just for that tiny little bit of space that's in between them. Examples in your body are blood and urine, and other examples, not in your body necessarily, is liquid water. The pressure exerted on an object by an incompressible fluid depends on multiple things. The first one, the main thing, is the depth of the object in the fluid. How much fluid directly above the object? So think of you going into a swimming pool. Well, if you're all the way at the bottom of the pool, you have all that extra liquid water above you. So that's one main way, one main factor, I should say, that influences the pressure. So the greater the depth, the greater the pressure, and vice versa. The density of the fluid also. The greater the density, the greater the pressure, and vice versa. You see here, you have an example of a man all the way at the bottom of the pool. He has all that added water above him that causes pressure against his body. And it all has to do with, again, collisions of particles of water against your body. As opposed to a midway here, he feels only this much pressure above him. If we take a look now at the density of matter, how tightly packed matter is, the amount of mass in a given space, that's the main definition for density, but it also makes a lot of sense with pressure. If you take a look at a gas where there are less particles pressing against the container versus a solid where there's so much more particles that are pressing against the surface. So depending on the density of a substance, this will vary the pressure. Like it says here, for the same volume, the denser the fluid, the more pressure it has. There are more particles pushing down on the surface. So we said before, we should eliminate solid from the equation. Solids are not even a fluid. If we take a look at gases and liquids, the liquid is always more dense and causes more pressure because it has more particles pressing against the surface. Now, let's look at compressible fluids. Compressible fluids are all gases. Because their volume can change, it is easy to squeeze a gas. The particles of gases move freely, so they easily take on the shape of their container. The one in our body, the example in our body is oxygen and carbon dioxide. And you see the image on the side here, it shows you. Because you have space in between gas particles, you are able to squeeze them into smaller areas. The pressure exerted on an object by a compressible fluid depends on the number also of particles. Of collisions due to particles involving the fluid particle. The number of particles of gas depends on the number of particles. So, of course, if you have a gas that's really light, like hydrogen or helium, that is less dense than, for example, carbon dioxide, the carbon dioxide will offer more pressure against the surface of a container versus helium or hydrogen. Of course, again, if you have more gas particles, then this will cause more pressure. So, first factor, like I was saying before, the number of molecules of gas there is. The more molecules, the more pressure, because the more chances of particles colliding. See, that word colliding comes back again, and vice versa. The volume and the temperature must remain the same for this to be true. Of course, you have to compare the volume, so the size, the container has to be the same. And the temperature. Of course, if we have high temperature, then the gas particles will press even more against the surface of a container. Now, I mentioned temperature before. The higher the temperature, the more the pressure, because the particles move more and more against the surface. They move even faster. Hence, collisions are more frequent and vice versa. You see in this image here, you have gases at a lower temperature versus this on the right, gases at a higher temperature. So there are bigger chances of collision against the surface of a container. This is very true in a hot air balloon. This is why as we go up in atmosphere, the fact that you have hot air, this allows the gas particles to keep on pushing against the surface of the balloon on the inside, and that's what keeps the hot air able to keep going higher and higher. The minute you turn off the heat, the air cools down, and right away the hot air balloon will tend to go down. The volume of the gas that it's in, the less the volume, the more the pressure, because more collisions occur in a smaller space. Again, it all has to do with, can it collide against the surface or not? So definitely if you're pressing down, like you see in the image here, if you're pressing down, you're causing more pressure on the inside. Then here's another image, the relationship between volume and pressure. You see here, we're adding pressure, we're adding a mass here on the piston. as we squeeze the gas, which of these three has more pressure? Well, yes, number 3, of course, because you have bigger chances of collisions of gas particles against the surface of the container. And I have to add down here, this applies to compressible fluids only gases. Now, this is very true in our bodies as well. The first principle of a fluid will travel from an area of high pressure to an area of low pressure. And we see that in our body when we breathe. We're able to breathe because of this law. The fact that there's a difference of pressure in your lungs allows you to inhale or exhale. You see in this image, it's a review actually from before. When you inhale, you are expanding the volume of your lungs. You're taking in more gas particles, oxygen, in your lungs. Since the volume increases, the pressure is decreased because you have more space. And on the opposite, here, as you exhale, the volume of the lungs decrease, and this is more pressure, so it forces air to get out of your lungs, carbon dioxide to get out of your lungs. Take a minute here and write this down. At first, the lack of air inside the lungs reduces the pressure inside the lungs. So air goes from a higher pressure, which is outside of your lungs, to the inside where the pressure is lower. Once the pressure is higher, like on the right, once the pressure is higher inside the lungs, we tend to exhale to reduce the air pressure. So our bodies are constantly doing this change of pressure. Our ears go through something very similar. We call the airplane ear. When you are going up in atmosphere, the pressure on the outside over here, the outside is on the right, is reduced. The air pressure, the atmospheric pressure around you, making the pressure inside your head bigger. And remember what we said, the pressure always goes from a high area of pressure to an area of low area of pressure. And so that's why you're going to feel your ears start to pop. And take a minute to write this down. At sea level, pressure on either side of the eardrum is the same. As we go higher in altitude, pressure is reduced around you. The inner ear has more pressure than the outer ear, causing a lot of pressure pushing on the eardrum from the inside. So people who are congested, for example, all the time and have a lot of fluid built up behind their eardrum can have a lot of pain because they have added pressure now. They have pressure from the fluids that are inside, like from the congestion. In addition to that, you have the pressure difference as you go higher in altitude. So that's why if you're planning to take the airplane, it is highly recommended to take an antihistamine or decongestant to keep your airways here and your ears clear from congestion. And the last example for today is your blood. Your blood moves because of differences in pressure in your heart. So as the heart squeezes, you have a smaller volume, and that means higher pressure. And the incompressible fluid, blood, will get out of your heart and into your body. You see? So you have all kinds of examples of pressure, of fluids, whether it's in your body or out of your body. Remember that fluids are only considered compressible if there are gases, incompressible if there are liquids, and solids are not even fluids. So have a nice day, everybody.